Hi, everybody. So up to this point, we have categorized different biochemical compounds, that is, compounds in living things. We have inorganic compounds, and the most important ones we talked about are water, oxygen, and carbon dioxide. They're inorganic because they don't have both C and H. They're missing one or the other or both. And then we have organic compounds, which have both carbon and hydrogen. And up to this point, we have talked about only one group of those, the carbohydrates, but remember there's lipids and proteins as well. And under carbohydrates, we say if they have one ring, they're monosaccharides. If they have two rings, they're disaccharides. And if they have three or more, they're polysaccharides. So that's where we are. Today, we're going to fill in the rest of this. We're going to move on to lipids. Now, carbohydrates are for energy, for doing, right? When you go to run, you go to carbohydrates, sugar, to go run. That's why you carbo load the night before. Turns out lipids are also for energy. When you think lipids, you should think fats and oils. They are also for energy, but they're for storing energy. So if you go to run, you're going to burn sugar to get the energy out of it so you can run. But if you've been eating a lot of sugar and you have a lot of extra to carry around, you're going to convert it into fat so that you can store it. And why? Well, it turns out that fats and oils, counterintuitively, don't weigh a lot. Think about that for a moment. What happens if you mix oil and water? The oil floats to the top because it's not very dense. So oil has a lot of calories, a lot of energy stored in it, but it doesn't weigh a lot per calorie. So if you have to carry around a lot of excess energy that you're storing, it's better to do that as a fat because it won't weigh as much as if you carried the same amount of energy in sugar. Okay, and so carbs are for doing, for immediate access for energy. Lipids are for storing energy. And we have oils. They're the ones that are liquid at room temperature. You have them in your cabinet. You've got olive oil and canola oil and corn oil. And then you have fats, which are solid at room temperature. And that includes a lot of the lipids that are in butter, in meats. Those are generally solid. And then there's a third called waxes that we won't talk about. All right, so the structure of lipids, if it's huge, it's scary looking. That's a scary looking molecule right there. It actually is pretty simple. You have one molecule here that is attached to three here. It's actually in the shape of an E, a giant capital E. This piece is called glycerol, and these are called fatty acids. Now, we won't spend a lot of time on this, but you need to be able to recognize, oh, that's a lipid. It's shaped like a giant E. It looks dramatically differently than a carbohydrate. Like a carbohydrate, it has carbon, hydrogen, oxygen, but carbohydrates have twice as many hydrogens as oxygens. Lipids don't, okay? But otherwise, they also look exceptionally different, right? The carbohydrates are rings all hooked together, or one ring, two rings, but the lipid is shaped like an E, and it has considerably less oxygen than the carbs. Okay, so if we look back at our table, we now have our inorganic compounds versus our organic compounds. The organic compounds include carbs and lipids. And then you have a very important group here. So the lipids aren't very heavily tested on the regions, and they're not a big focus of what we're doing. But the next one, like carbohydrates, is, and that is proteins. Proteins are the building blocks of your muscles and a lot of parts of your cells, and they're important for controlling chemical reactions in your body. You're a walking, talking pile of chemical reactions. So the fact that proteins are important for controlling that means it's really essential for life. I mean, these things are important. They keep you going. So proteins are exceptionally important for lots of different things. The color in your eyeball, that's a protein. It's a colorful protein, makes you look a certain way. The material that makes up most of your hair is a protein. You are made largely of proteins. These are long chains of something called amino acids. Just like a polysaccharide is made up of long chains of monosaccharides, Proteins are made of long chains of something called amino acids. Same idea, right? You got one monosaccharide or two making a disaccharide or three or more making a polysaccharide. Instead of working with the rings, we're going to work with something called an amino acid. So you need to know the amino acid structure. And the amino acid structure is that. It's not a big scary ring. It's actually pretty simple. Take a look. We've got a carbon right in the middle, and then we have four things hanging off of it. And that's the way I want you to think about this. We've got a carbon in the middle, and we have four things hanging off that carbon. We have on one side a nitrogen and two hydrogens. Whoa, nitrogen, we haven't seen that in anything. Carbs have CH and O, twice as many H's as O's. Lipids have CHO, not twice as many H's as O's. But proteins, you can see them a mile away because you now have a nitrogen. You have a nitrogen in there. And so that group, that collection, N and two H's, is called an amino group. On the other side, you have a COOH, a carboxyl group, and on the bottom you have a hydrogen. That's true of every single amino acid you see. It'll be exactly like that. The only thing that's different is that we call it the radical, and it just is different from one of the 21 amino acids to the next. So that's what makes them different. So we have an amino group, a carboxyl group, and the part that varies called the radical. So let's take a look. This is an amino acid. That radical could be a hydrogen, it could be CH3, there's all sorts of things could be there. Whatever it is, the rest of it's the same. We have an amino acid plus another amino acid. And if we put them together, we get two amino acids. We call it a dipeptide. Now listen, if I were in charge, I would call an amino acid, I wouldn't call it an amino acid, I would call it a monopeptide, right? Monopeptide and dipeptide, that's not what it's called. This is an amino acid, which you can think of like a monopeptide, and another one, a monopeptide. And if we put them together, we will get a dipeptide. The reason, never mind. So we have two amino acids that get hooked together into a dipeptide. So single one is amino acid, not monopeptide. Two is a dipeptide. And three or more, we'll get to that in a moment. When we combine these two amino acids, we take out an OH here, we take out an H here. That OH and that H become water, and we form a bond directly between the C and the N. So the formation of a dipeptide is by what chemical reaction? Dehydration synthesis. We've removed water, dehydration, to join something together, make something bigger, synthesis. So taking two amino acids to make a dipeptide is done by dehydration synthesis, just like taking two monosaccharides and combining them and remove water to make a disaccharide. That is also dehydration synthesis. Same reaction, but this time instead of dealing with a monosaccharide and a monosaccharide and a disaccharide, we're dealing with an amino acid, monopeptide, and an amino acid, monopeptide, to make a dipeptide by dehydration synthesis. What would happen if we hooked another one on there by removing water? And so once you combine the three amino acids together by dehydration synthesis, you're going to get a polypeptide, 1, 2, 3, and this time you'll get two waters because you've removed one water here and one water here to get the polypeptide. Now, how is it? It's really hard to look at that and see, is that a polypeptide or a dipeptide? Now, let's figure out how we can easily classify it. First of all, it has C, H, O, and N. So automatically, you know it's in the protein category. And it has 1, 2, 3 N's. That's 3 or more. Every amino acid has one nitrogen. So an amino acid is one nitrogen. A dipeptide has 2 nitrogens, and a polypeptide will have 3 or more nitrogens. Proteins there are billions of kinds of proteins. Maybe that's an exaggeration. There's millions anyway. There's lots and lots of different kinds of proteins. And what makes one protein different from another is the order of their amino acids. Remember that if we look at the amino acid, we look at the amino acid. Every amino acid is going to have an amino group, a carboxyl group, and a hydrogen. The only thing that's different on every single one is that R, and there's 21 different kinds. And you can have chains, polypeptides, that are thousands of amino acids long. And if you have that, you can put those 21 in a whole lot of different orders, and you end up with a whole lot of different kinds of proteins. The order of amino acids is going to change the shape of the protein, and that protein will behave differently depending on its shape. We'll talk about that more next time. So we are now left with this. We've got biochemical compounds can be inorganic if they don't have both C and H, organic if they have both C and H. Organic compounds can be carbs, lipids, or proteins. And carbs come in the single ring monosaccharides, the double ring disaccharides, the triple or more poly. Lipids can be fats, oils, or waxes, and proteins can be amino acids, monopeptides, dipeptides, or polypeptides. How do you tell the difference between carbs, lipids, and proteins? Carbs and lipids have C, H, and O, no N. So if it has an N, you know you're in the protein category. If you have C, H, and O, then if there's exactly twice as many H's as O's, it's a carb. If there isn't, it's a lipid. Another way to tell the difference, these are shaped in rings. This looks like an E. And that is all the biochemical compounds you need to know for the course at this point.